Hello everyone, welcome to another episode of Material Matrix. Welcome. Tonight, we explore graph neural networks, discover how GNNs revolutionize materials like science, analyzing molecules as networks to predict properties, and design new materials. They excel where traditional methods fall short, like driving smarter, faster innovation. What are the fundamental principles of graph neural networks, particularly in the context of material science and chemistry, and how do they differ from traditional machine learning approaches like
graph neural networks? So GNNs are like a special kind of tool that helps us understand and predict things about materials and molecules by looking at them as networks. Imagine a spider web where each point is a little dot, like an atom connected by strings, like bonds. So GNNs can take these webs and analyze them to find out how the dots and strings interact, which is really important in chemistry and materials science. The fundamental principle of GNNs is that they can work directly with the graph structure of molecules and materials. So this means they can understand how the different parts are connected and how they influence each other. Traditional machine learning approaches like convolutional neural networks, GNNs, are more like looking at pictures in a grid format, which works well for images, but doesn't capture the unique connections in a molecule structure as effectively. In short, GNNs are designed for the irregular shapes of molecules. So while traditional methods are better suited for regular shapes like images, this ability to handle complex connections makes GNNs particularly powerful for predicting properties of materials and helping in the design of new materials.
Can you elaborate on the message passing framework within graph neural networks and how it actually facilitates the incorporation of geometric information in the analysis of molecular structures?
The message passing framework in graph neural networks, GNNs is just like a team of friends, passing notes to each other to share information. Each friend represents a node or atom in a molecular structure, and the nodes they pass are the kind of messages that contain important details about their connections or like bonds, and their own characteristics. In this framework, so each node sends and receives messages from its neighbors. This whole process helps the nodes understand not just their own properties, but also how they relate to the other nodes around them. For example, if one atom is connected to another, it can share information about its own properties, which really helps the other atom learn more about its environment. Incorporating geometric information basically means that these messages can also include details about the distances and angles between the atoms, much like how the layout of a city can actually affect how people interact. By considering not just the connections, but also the spatial arrangement, so GNNs can better analyze molecular structures and predict their properties. Overall, the message passing framework allows GNNs to capture the complex relationships and geometric details in molecular graphs, making them so powerful tools for understanding materials and designing new ones.
What state-of-the-art GNN architectures have emerged in recent years, and how do they enhance the performance of predictions in specific applications within chemistry and materials like science?
In recent years, several advanced graph neural network GNN architectures have emerged, each designed to tackle specific challenges in chemistry and materials like science. These architectures really enhance prediction performance by better capturing the complex relationships and properties of molecular and material structures. So one notable example involved using GNNs to predict the outcomes of solid-state in synthesis. So developed in this application, GNNs can represent the starting materials as a dense graph, allowing the model to analyze how these materials interact during the reaction. So this approach improves the accuracy of predicting what products will form, which is so crucial for designing new materials. GNNs have also shown pretty significant promise in various tasks, such as predicting the properties of molecules and materials, accelerating simulations, and identifying synthesis risk. They often outperform traditional machine learning models like densely connected neural networks because they leverage the whole unique graph structure of molecules and materials, giving them access to all relevant information needed for accurate predictions. So overall, the development of these state-of-the-art GNN architectures is really paving the way for advancements in virtual materials design and enhancing our ability to understand and create new materials in chemistry and materials like science.
Could you discuss the types of datasets commonly used in GNN research for chemistry and materials like science, and how they contribute to the training and validation of these models?
In GNN research for chemistry and materials science, a variety of datasets are commonly used, each serving a specific purpose in training and validating the models. These datasets can be thought of as the building blocks. that help GNNs learn and improve their predictions. One type of dataset focuses on molecular structures, which actually includes information about different molecules and their properties. These datasets are essential for teaching GNNs how to understand the relationships between atoms in a molecule and how those relationships influence properties like stability or reactivity. Another category includes datasets or crystalline materials, which represent the orderly arrangement of atoms and solids. So, while there are many datasets for molecules, the availability of comprehensive datasets for crystalline materials is more so limited. This can make it really challenging to apply GNNs to these types of materials, as they may not have enough examples to learn from. Additionally, some datasets contain experimental data, which can provide real-world insights into how materials actually behave. This information is crucial for validating the predictions made by GNNs, so ensuring that the models are not just accurate in theory, but also in practice. When there isn't enough data available for a specific task, GNNs can leverage these studies learned from larger, more generic datasets. This means that the knowledge gained from studying one set of materials can be transferred to other tasks, allowing GNNs to make predictions even when data is so scarce. Overall, these datasets actually play a vital role in the development of GNNs, enabling them to learn from diverse examples and ultimately enhancing their ability to predict properties and behaviors in both chemistry and materials like science.
What are some recent applications of GNNs in chemistry and materials like science that highlight their practical significance? And how do these applications demonstrate the advantages of using GNNs over traditional methods?
Recent applications of graph neural network strands in chemistry and materials like science showcase their practical significance and advantages over traditional methods. One prominent area is materials like simulation, where GNNs can effectively model and predict the properties of materials, including those with complex structures like disordered or amorphous materials. Traditional methods such as quantum mechanical simulations so often struggle with these types of systems, making GNNs particularly valuable. Another application is just in the screening and design of new material. So GNNs can analyze vastness of molecular and material structures to identify promising candidates for specific applications, such as catalysts or battery material. This capability allows researchers to explore a broader range of possibilities more efficiently than traditional methods, which may require more time and computational resources to evaluate each candidate. So individually. GNNs have also been successfully applied in predicting synthesis routes, so helping scientists determine the best ways to create new materials. This can significantly accelerate the development process, so as GNNs can provide insights that traditional approaches might miss, especially in complex reaction networks. Overall, these applications highlight how GNNs leverage their ability to work with graph-structured data, giving them full access to the relevant information needed to characterize materials. So, this unique capability allows GNNs to outperform traditional methods in various tasks, making them an increasingly important tool in the fields of chemistry and materials like science.
Well, that brings us to the end of a truly insightful discussion. A huge thank you to everyone who joined us today. We've explored how graph neural networks, or GNNs, are revolutionizing our understanding of materials and molecules. It's pretty clear that these specialized tools excel at analyzing and predicting properties by treating structures as interconnected networks of atoms and bonds, so overcoming limitations of traditional methods when faced with such complex data. The core of their power lies in the message-passing framework, allowing information to flow between individual atoms, which greatly enhances our understanding of molecular interactions and properties. But we saw how recent advancements in GNN architectures are significantly improving their predictive capabilities. So from forecasting molecular properties to aiding in solid-state synthesis and materials design. Ultimately, GNNs are proving their practical significance in real-world applications like materials like simulation, new materials like screening and predicting synthesis pathways. By efficiently analyzing complex data and reducing computational costs, they offer distinct advantages over older approaches. So, thank you once again for being with us. So we hope you gained a clearer picture of the exciting potential of these powerful techniques in materials science and chemistry. Until next time, so stay curious.